All right, great. Thank you very much for coming. Yes, so today I'll quickly go through defragmenting Ethereum or defragmenting the world computer, how we get to better cross-chain integrity with controllers. So this talk is really focused on controllers and what controllers actually buy us in the real world, so that instead of the ecosystem currently feeling like 15,000 different chains that are all honestly not connected to each other, that it feels like actually one ecosystem where users and applications can easily roam and sort of across this multi-chain world that we're clearly seeing at the moment. And this is, a lot of this technical work is motivated actually by the fact that I think I cannot explain the current state of the ecosystem to anyone in the real world. Like my parents clearly won't understand how we've arrived in a situation that is honestly less convenient to use than many of the existing systems, because you have to have, I don't know, 6 different wallets. They all sometimes work on some systems, but on others, none of them have privacy and so on, right? Like, so how do we actually fix this, and how do we get cross-chain integrity with controllers? So the next generation of interoperability really requires a paradigm shift from asynchronous message passing to managing shared state integrity. At the moment, we're living in this world of asynchronous message passing, right? Like when you, for example, send an IBC message from chain A to chain B, you are doing an asynchronous message passing action. Or even like when you move from Ethereum main chain to Optimism, this is an asynchronous action. The controller architecture fundamentally provides a framework to solve the core problems of provenance, privacy, and composability that limit current protocols, whether this is IBC or sort of our patchy framework of Ethereum interop. Okay, so starting with a fundamental trilemma, like what's actually the problem? Why is this hard to do? Well, in the CAP system, CAP Ethereum and distributed systems, we sort of have 3 properties. We either are consistent, or we're available, or we are partition tolerant. And you can generally only pick 2. So what does the multi-chain ecosystem actually pick at the moment? Well, we pick availability and partition tolerance. So it does not mean that we currently have guarantees for global consistency. And when you don't have guarantees for global consistency, the core challenge becomes, how do you manage this shared state integrity? Where like forks happen all the time, or inconsistency can arise naturally, right? Like we never really built the interoperability solutions around this idea that like many of these systems may spin up at any given moment, may disappear at any given moment, may become unavailable at any given moment. So we really, like with this actual fundamental design constraint in mind, we have to come up with like what is the correct or like what is the best way to actually make to defragment the sort of multi-chain ecosystem. And actually, just a curious show of hands, who here still remembers that you like would run defragment on Windows hard drives? So yeah, this is pretty much the same idea, sort of conceptually speaking. You want to make the system faster, like more nicely to use, or nicer to use, by actually from time to time making sure that state lives in the right places. But let's start with a past critique. And I'll focus here on IBC, mostly because IBC is actually like by far the most battle-tested and well-scoped and well sort of like designed system that was trying to solve, or that is trying to solve, interoperability in this multi-chain ecosystem. And maybe just quickly, when I say chain, I really mean whether you're talking about an L1 or an L2. These are very arbitrary distinctions. To me, these systems are all just fundamental chains. They're fundamental to sort of like ordering domains. So when I say chain, you can interpret chain as to mean an L2 or an L1. Maybe this will be next year's talk of how we should stop calling these systems L1s and L2s, and how we should stop confusing everyone with these like very nonsensical terms that sort of from a fundamental technical perspective mean very little. But yeah. Let's start with IBC and sort of like what worked, what didn't work. So IBC made some tactical mistakes. I mean, it was a very complex problem, or it's a very complex protocol that was honestly over-engineered. And in its defense, I can only really say that IBC was ahead of its time, i.e. it was designed when the multi-chain was designed in 2017, 2018, when we really didn't see sort of the multi-chain problem at scale. Like we didn't have Optimism, Arbitrum, and all these like 20 different rollups that actually need to talk to each other. This was much more of a conceptual idea, like we are going to move to this world and we should think about how interoperability will actually work in practice. As a result, you also ended up with a bunch of primitives that honestly, in retrospect, were like provided suboptimal trade-offs. So now, sort of, with the benefit of hindsight, we can actually think about how do we design a protocol that is more adapted for the problems that we actually see at the moment in the real world. Yeah, some of the strategic mistakes were that IBC never really addressed the problem of path-dependent tokens, right? And sort of like when you think about it, this is actually something I think that a lot of people don't fundamentally sort of internally understand. It's when you send an asset from Ethereum to Optimism to Arbitrum, or it matters, like the path matters. So like you go from Ethereum to Optimism to Arbitrum to zk sync, and now you have some ETH there. This is not the same as the ETH that you send from Ethereum to Arbitrum to Optimism to zk sync. Like these two systems are fundamentally, like the two assets are fundamentally different. And there's sort of like, you have to think about how you provide a way to do automatic path unwinding for not just asset transfers, but more complex state transfers. And I think we had a lot of talks today about sort of relating to privacy, right? One of the big problems is none of the current ideas on how do we actually fix this, and I call this generally a sucking chest wound in our ecosystem that we're trying to put like Scotch tape over. How do we fix this problem of fragmentation in the ecosystem? None of the current proposed solutions sort of like provide for native privacy. And I think we have to be very realistic here that if we want to get the real world on board with these systems, we must provide a way where we can have proposable privacy guarantees, where you can, for example, implement things like private bridging. Because sort of otherwise you are fundamentally always going to be limited to not being able to, like, that you always have to unshield when you want to go from system A to system B. And this is never going to work at scale. Yeah, so outside of IBC, really there haven't been many sort of like well thought out end-to-end design protocols. There have been some few derivative solutions. I mean, Polkadot tried some things. But again, no over-architecture was sort of proposed and actually deployed. So with this, let's come to controllers. So controllers are all about thinking about how state moves around the multi-chain ecosystem and sort of who's in charge of ordering certain actions that can update state. Yeah, the controller architecture just fundamentally introduces new primitives to manage shared state integrity across sovereign domains. And like, again, like all the rollups, they're sovereign domains, really, when you think of them from an ordering perspective. Yeah, just sort of a very brief comparison. With IBC or the current message passing paradigms, we really live in this like asynchronous message passing paradigm. With controllers, you're thinking much more about state. You're thinking like, does the state layout work? And like, how do you come to agreement over shared state integrity? Yeah, you think of transferable resources, you have arbitrary state and logic, and really when you think of the provenance, it is not a linear path trace anymore, but rather a directed acyclic graph, and it supports privacy. Okay, coming to the core concepts and guarantees that controllers actually provide you. So the anatomy of the system, and it all starts with a resource. You can think of a resource as a generalized transferable object that bundles data with programmable validation rules. It is somewhere in the middle of like a UTXO and an incount model. This is sort of, it comes very much from the reasoning of like you want to have native privacy, and very quickly your models start looking like UTXO models because this makes it much easier from a sort of practical perspective. Beyond the resources or the resource logics, you have the controllers. And controllers really are, traditionally you'd call them blockchains or sequencers, right? Like the Optimism sequencer, that's one controller. The Ethereum main chain, that's one controller. And the controllers are the authoritative state machines that order transactions for a specific resource, preventing double spending. And then you have resource labels, i.e. how do these resources move through many different controllers. You can think of this sort of like as a passport with many different stamps for how each resource has moved through the ecosystem, and as a result you get this like provenance record or controller DAG. And so the last thing, which is sadly cut off from these slides here, is that it has a current terminal controller. You can, for example, think of ETH. Like when you move ETH from Ethereum main chain to Arbitrum, you're currently delegating a resource to now currently the terminal controller is actually on Arbitrum. Or like the Arbitrum sequencer is now the terminal controller here. So what is a core guarantee? Well, you get consistent controller labels. And what this really comes down to, it is too expensive to enforce perfect history. So CGL guarantees sort of like try to do the next best thing. As is, they try to say that, or they say that if a resource's history is inconsistent, there must somewhere be a Byzantine controller that is responsible and clearly identifiable. Thus, you make trust very explicit and actually very easily checkable. Okay, now as the next thing, we come to the affordances here. Like what affordances does this controller system bring you for defragmenting the world computer? Or actually making my co-founder Chris gave an interesting talk on making the world computer a reality so that rather than it feeling like an incredibly messy ecosystem, there's just like one interface you interact with, and this could be then running on many different systems under the hood. Yes. So the affordances are, you get to move arbitrary state, and this really extends beyond simple token transfers. In all the discussions really at the moment, we are thinking, how do we make simple token transfers work? And I think this is probably okay for maybe the current state of things, but this is certainly not okay if you think like, oh, I'd like to create a CDP with Maker, and then I'd like to move now my CDP to a specific other system where I would like to use the CDP as collateral, but I want to maintain the same sort of liquidation rules. This becomes, and sort of the simple answer, the simplistic answer to this is, well, just unwind your CDP on sort of system A and just recreate it on system B where you want to use it as collateral. This will never work at scale because you have to keep unwinding all your positions to essentially break down into the raw asset types. And for example, when you think not of this as a CDP, but rather as a loan agreement for like a real-world mortgage, you're not going to sell your house every time you want to move like to a different system, right? Like you're not going to go, oh, shit, I want to move my mortgage from Ethereum main chain to Arbitrum. Let me just quickly in the middle sell my house, get the cash, move the house to the other system, and rebuy it all in an atomic system, right? In an atomic transaction. So the basic mechanism is that with research logics, you can move stateful applications, such as CDPs, because you can encapsulate these like very complex stateful applications within a single resource. And when a resource moves to a new domain, its logic travels with it. And then the new controller becomes responsible for enforcing this specific logic. This also prevents the problem that like you need to start redeploying all the applications on all these systems. At the moment, you can rather have like you deploy your application, for example, on Ethereum main chain, and then when you want to take your resource logic to another system, it's not limited to whether like someone has deployed Maker to Arbitrum. Like it's a single unified application really that exists across the world computer rather than many different deployments of the same application that are fundamentally not interactive. Yeah, the example that I always like to think of it is a portable CDP, where you can move it from Ethereum to some other system without having to unwind it and rebuild it on the other side. You also get provenance simplification. How does this work? Essentially, it solves the problem of some resources may be long-lived and may move across sort of the multi-chain ecosystem or the multi-chain universe for, I don't know, 500 times. You need some way to condense the history graph. And this is what the provenance simplification mechanism actually allows you to do, so that you don't actually have to carry around sort of the never-ending history of it. And sort of at a very high level, controllers can essentially endorse subsegments and then you get a reduced proof, and then you just attach the reduced proof rather than the entire history. Yeah, this is what fundamentally enables. It generalizes the IBC problem of simple unwrapping to arbitrary state and arbitrary network topologies. This is, by the way, also just way more inherently scalable, because one of the big problems with a lot of these interop systems is that you always have the same routing hub. Like, you always would have to go via the same system, and these sort of main routing hubs then become choke points. This doesn't have this problem. And lastly, you get shielded bridging. You get actually privacy as a first-class citizen, which, again, I think if we want sort of the real world outside of this room to actually start adopting the technology that we're building here, we can't say, well, all your neighbors know exactly when you went to the doctor and like what kind of medication you buy at the pharmacy. This is just not going to work in practice. This also makes the system very simple, because essentially the mechanism for this is resource logics can either be authorized by simple signatures, or they can be authorized by ZKPs. So instead of requiring the entire public data for validation, you just have the ZKP. And honestly, actually, in the ZK world, this is much easier to do, because the controllers just have to verify the ZKP. They don't have to verify anything else. Yeah, and as a result, you actually get true end-to-end cross-domain privacy, where you don't have split shielded sets. Yes, so controllers really, it's an all-encompassing solution to solving Ethereum's fragmentation problem. And I don't know how many of you were at L2 Interop Day yesterday, but I mean, we spoke a lot about these things. The problem is like they are Scotch tape on a sucking chest wound. And I think that we've got to be sort of very practical about this is not going to be fixed by applying small band-aids. This actually requires us to think about how we actually do this in practice at scale. So yeah, controllers give you all of this. Yeah, and as a result, you get a unified fabric for the L2 or the interchain ecosystem to do this with. Oh, I'm at 40 seconds. Fundamentally, it eliminates asset fragmentation. So rather than having a single canonical ETH, so you just end up with a single canonical ETH resource, and when you move it to a new controller, you just update the terminal controller label on that specific resource. You got also trust minimized bridging security, because the entire system just relies on light client proofs and not on sort of the incredibly shitty multi-sig bridges at the moment, and you get composable privacy. Yeah, it's sort of a foundational paradigm shift here, where we get generalized interoperability for arbitrary state and applications. It manages historic complexity quite well, and it ensures native privacy through ZKP first design. Yeah, if you're interested in this, I'll link the paper in a second. But really, this is all about enabling the vision of an internet of sovereign domains, where many systems may interact with each other, some spin up, some spin down, but sort of fundamentally this is supposed to, and like we should aim to have this feel like a unified ecosystem. So thank you very much.